my turn. First of all, do you guys agree that those matrices on the bottom are right? Do you agree that the signs in front of them are right? Are you sure? Because how did we get those signs? And the third column is going to be positive, negative, positive, negative, positive. Positive times a negative times a positive. Now, did I change or should I change this -8 to be a positive? No. But I multiply it by a positive, if that makes sense. So then when you guys kept on going to solve, hopefully, well, wait, what was the next step that you guys were supposed to do? Find the determinants of each of the 2x2s, right? So main minus opposite, -42 minus 12, ended up being -54. 21 minus 16 ended up being 5. Well, we could just do -8, right? Positive times a negative is a negative. And then we -9 minus 24 would be -33. And what ended up happening when you guys went ahead and solved all that? Ooh, 151. Now, what was I talking about when I said you could double check it, triple check it? Another way. Use a different column, use a different row, but what was the other unique to only 3x3s? Oh. Can you guys matrix real quick? There are just a few of you that are really good at mental math. I'm just saying this is a way for 3x3s you could go. What's the original matrix? You guys reading this way? -3, 4, 2. Okay. Do you remember how much I tack on? 2 extra rows. So I need 4, 1 to hit and 2 to hit. So then I'm going to do the 3, 6, 4, 4, -7. Oh, there's no negative? Where? Oh, next to the 3. Thank you, thank you. The mouse was close and somehow I ignored it. Okay, so main, that would end up being -9 times -8 would be 72. Second main would be 16. The third main would be -84. Yeah? Minus opposite. 24 and 8. Ugh. 48 and 4. That'd be 2 and 3. Is that 192? Nice. Careful though. It's minus all of these. Be 21. Oh, gracias. That was close. And the last one, 24, right? Because I'm still. Oh, isn't that a negative? Sorry, my red covered it. A negative times a negative. Lo siento. So you end up with 88 minus 84 plus 192. I'm just kind of like grouping it as I go. And then that'd be minus 45. That's going to end up being 4. 4 and 192 is 196. 196 minus 45 ends up being 151. Done. Dun, dun. But that only works with 3x3s. Lo siento. This works with anything, huh? Yeah, right? Because there's so much that could go wrong. I mean, there's so much that could go wrong in this one, but you get to break it down. What do you guys think about? I won't go harder yet. Let's get this guy. Then, how would we do this? Big Mama problem, not a packet. Okay. Hold on, this isn't the Big Mama one. This is easy. How do you do this one? It's a little baby one. All we got to do is AD, right? Minus negative 14, which would be plus 14, yeah? Is this that bad? No, because then all you have to do is go ahead and FOIL. And you're just going to solve by factoring, yeah? Okay. So they could try to throw in some algebraic something, something, something just to keep you on your toes, but otherwise we end up with, as long as you keep your wits about you, these should actually be pretty easy, yeah? Okay. Do you remember from yesterday, though, when I said this could get hard? 4 by 4, 5 by 5, 6 by 6. It's just going to get worse and worse and worse as we go. Why did it just get harder? When you go to make your cofactor, aka when you go to make your minor with the right sign, you're going to have a 3 by 3 remaining. So let's be strategic. Look at the directions. Use the row or column you get to choose that makes it the easiest. What row, what column looks best? And why do I only have it written twice? Yeah, check out that guy. What's going to be nice about him? Remember, you take an entry times, right? Couldn't I take a 6? Positive, negative, positive, a positive times a 6? And couldn't I multiply it by its determinant, right? The determinant of what remains, which would be the 736501707. And then what's the next term going to be? Positive, negative, positive, negative. A negative times a 3. The determinant of that guy, which is messy, I know. I'm just showing it to you for right now. But why did I only write it twice? 0 times anything is 0. Forget that. 0 times anything is 0. Forget that. Ooh, I like that third column. Doesn't mean it's an easy problem still, but it's easier than it would be if those hadn't been zeros. Could the third row have been nice? Yeah, I guess. I mean, there are 2 1s, but there's only 1 0. If you notice, we're going to have 3 by 3s that we have to break down. So, ooh, those nasty 3 by 3s. We're going to have to figure out how to do that. But if we can at least cut down 4 entries to 2 entries, life just got a lot easier. Now, I'm going to go ahead and write what we've got. We have 6 times the determinant of 736501707. And as I'm writing out what we have, I want you guys to be looking at these matrices and trying to figure out, we can't just do main minus opposite. We have to actually do each of these 3 by 3s individually. So let's choose a row or column that makes this nice and neat. For the first matrix, we can't just do main minus opposite unless you want to write 2 more next to it and then have that twice and hope that you make no mistakes on mental math. Otherwise, you have to choose a row or column. Who do you want to choose? Yeah, look, he has zeros. Now, for the next guy, I'm not so sure. Maybe the second row. I think that's, it has 2 1s. I guess that's kind of the easiest. Yeah, you could do 2 1 3. That's true too. But we're going to have to take those 3 by 3s and now do the process of finding the determinant within this problem of finding the determinant. John? Hold on, I'm trying to track. Oh, what did I cross out? I have no idea. What did I do? It's one of those mornings, I guess. Took me a second to figure out what you were saying, but then, yeah, it's pretty obvious, huh? Aw, that just got a lot less fun. So some of you are like, well, I would have really loved the whole zeros thing, so maybe you don't want to use these guys because they're going to cross off the zeros, but oh well. So we have 276151. It's kind of a give and take in the sense of if you choose the nice one so you don't have to worry about the 2 zeros and their determinants, well, you're not going to be able to use the zeros in the smaller determinants. I don't know. It's a give and take. 1, 2, 3, you really want that one? Thomas really wants that one. All right, we'll do that one. Now, guys, I'm going to go ahead and zoom in so I can write smaller. Because right now I'm not going to be able to write very small and it's not going to be very nice. But now, do you guys agree with how I finally set up the problem? Lo siento, it took so long. Okay. Does it make sense? Nope. Because if you look at the beginning chart, I did it a while ago, Carl, but let me zoom out really quick. We just need to get solving this problem. Remember, you start with a positive, positive, negative, positive. Yeah, there you go. So let's zoom back in. Let me scroll down. let's tackle this guy. 6 times. Nice thing is, now that we have a new determinant, we're not looking at the 2's placement in the original. We're looking at the 2's placement right here for the sign. So does it make sense why I'm going to put a positive 2 regardless of what was up above? He's in the positive spot of the new matrix I'm finding the determinant of. Why am I doing the 2? Because Thomas said so. Okay, so if I do the 2, do you guys agree I have 5, 1, 7, 7 left over? Minus 1 times. Okay, double check. I already made a mistake, so make sure I'm good. So far, so good? Let's save a little bit of space right here. What am I doing? Now whose turn is it? Okay, but pause. Any questions on the first one? Because if you're not caught up with me yet, you'll just get more behind. See how I chose the 2 in the positive spot, cross, cross, take the rest. Chose the 1 in the positive negative spot, take the rest. Chose the 3 in the positive spot, the rest. Okay, so then positive, negative. Choosing the 1. Woo. You guys get ahead of me because there's a lot of double checking that needs to go on this one if I'm doing it fast in class. I'm turning up the air, but you guys start solving. Main minus opposite. You guys know what to do. I'll come behind and then we'll double check each other. Well, why can't it takes so much longer if you actually try to use a calculator to solve this by hand. It's main AD minus opposite BC. Yeah. Is anybody else going to distribute the 6? No? Oh. Okay. It's okay. We should still end up at the same place, right? Okay. You guys ahead of me yet? Shh. Shouldn't be doing it that way. Oh, okay. Not 20 minutes, maybe 10. I think that's 336. I think that's 434. Oh, 414? No way, really? 460 minus 46. Oh, yeah. 460 minus 46. Good call. Something nice. Do 84 minus 12 will be 72 minus 42 will be 30 minus, that's going to be 64, 74, 78. $198 and 30. Did I do something wrong? Oh, I'm good. And then that'd be negative 48 and then negative 168, right? A lot of mental math. I mean, these ones, I made a silly mistake on that. I did 460 minus 26 instead of 46. We can do like 10 times 28 and then add 2 more 28. So you can do like 20 times 23 and then take away 2 23s. I don't know. Or you can do 2-column multiplication, but ugh, that's gross. Is that good according to the... Nice. Go team. Was it possible? Yes. Was it super easy? But what made it nice? The zeros. Now, hold on, pause. The zeros, either you can make it nice right away so you have half as much to do, or, once again, in case you weren't tracking on what I was saying, or you could have left the zeros in and chosen a different row or column. I would even maybe do a different row or column, because then the zeros would be present in all your little 3x3s. You would just have 4 3x3s to do, but you would have nice little zeros in between, which might have made it actually faster to go the other way. But either way, you end up with multiplications that you have to go ahead and do and solve. Kiddos, quick heads up on this test that's coming on Tuesday. Remember, if you don't remember, I said there is a calculator and a non-calculator portion. Tuesday. Because what are we doing right this second? We're done with 8-4, so we're saying, hey, here we go, 8-5. Yeah. Yeah. I would have done the 1-5-1 both times, but Thomas really wanted the 1-2-3. That was really 2-1-3, and so we just did one of each. Okay. That's true. Because then you could do like 6 7s minus 2 7s, or yeah. I saw it. Guys, this section is going to feel super random because basically it's like, oh, hey, what can we use determinants for? Oh, hey, what can we use matrices for? Some word problems maybe, but not necessarily. We did that one dairy milk one. The milk in the convenience store. Here, I'll look. Ooh. I don't see any word problems. Go team. Do you see something that said coding? Ooh. Coded messages with matrices. No, that's the end of section 5. Okay, let me give you a second. The first thing that you're talking about is Cramer's rule. Which, like many things that you've seen recently in math, is easiest on the easiest types of problems. Sadly. But remember, some of the things you're learning, they might not be easy to do by hand, but possibly they'd be easier to code in. Or to code with. Maybe something to keep in mind. So Cramer's rule is going to look like a complicated way of solving a 2x2 system in the sense of 2 variables, 2 equations. It's going to look like a complicated way of solving, but remember, it can be generalized to be used for a 3x3, a 4x4, a 5x5, and maybe by hand it would be disgusting to do, but maybe, just maybe, the programming might be simpler than other ways that we've solved systems before. If you do go into computer science, or in programming in general, efficiency is a big key word. Talk about efficiency in Calc BC a little bit. Not that it's a calculus topic, but efficiency, how efficient a program is. If you guys search, here's just a silly example. If you search on the App Store for some sort of birthday app, you know what I'm talking about? Some sort of app to keep track of people's birthdays, give you reminders, etc. If you search, okay, never mind. What's something else you guys might look for? Let's just do the birthday app. It makes sense. Okay, if you go looking for a birthday app, how many are going to pop up? A lot. So, how do you choose one? Maybe look for the ones that are free first. You probably look at the user screens to see if you actually like how it looks. If it's super annoying with lots of ads, you're like, no thank you. And then at some point, you probably look at the reviews, right? Okay. What makes an app nice? Maybe it's design. Maybe it's features. But isn't a lot of it how fast it goes? If you have something that lags, are you going to keep it for very long? Probably not. Why would it lag? There are lots of different reasons, but one way could be, yeah, it does the exact same thing as another program, but it does it in a less efficient way, aka its programming is messier, is longer, makes the processor work harder. The better the programming, the more efficient the process, the faster. Yeah, there are many different reasons, but I said one reason might be. But if on your phone one app is slower than another app, that's not your phone anymore, unless you're on different Wi-Fi networks. But anyway, or you have something random like T-Mobile. But anyway, just kidding. Doesn't T-Mobile have unlimited, so we can't totally diss them? We can diss Sprint because it stole the Verizon guy and made this whole dramatic thing about advertising. But anyway. Just like capitalizing on drama. So, long story short, Cramer's rule is just another way, which might not seem very helpful to you, but whatever. Someone somewhere thinks it's helpful, so let's just see how it works, because it all builds on determinants. And once again, it's easiest on the easiest type, so we're just applying it to the easiest one so that you see how it works. Cramer's rule says, wait a minute, where do these little matrices come from? Hold on, pause. First of all, this is a system of equations, yeah? When we solve a system, what are we usually looking for? X and Y. So, Cramer's rule says, hey, here's a way to get X and here's a way to get Y. And guess where it comes from? Determinants. Here's a way to find X and here's a way to find Y. But let's figure out where these matrices came from. So, for X, well, first of all, hold on, aren't both of their denominators the same? Okay, both their denominators, just take what from up above? We can say a variable in a system is going to equal the determinant of, who is A1, B1, A2, B2? Oh, come on, what do we call those? No, constants are the C1, C2. The coefficient matrix, you guys are killing me. The coefficient matrix, right? The coefficients of the variables, true? So the determinant of the coefficient matrix for whatever variable you're solving for, whether it's X or Y, if it was a 3-dimensional Z, if it's a 4-dimensional W, you're going to take the determinant of the coefficient matrix on the bottom, and what's going to be on the top? Uh-oh. The determinant of... What's going on? What was eliminated from the coefficient matrix and replaced with the constants? The X ones. You're solving for X, you eliminate the X's and you put the constants in its place. The Y ones, you eliminate the Y's and you put the constants in its place. So it would be the matrix formed by replacing vars, whatever var you're searching for, coefficients with the constants. There you go. That's Cramer's rule. Doesn't matter what size the system is. You can always take, to find the variable, the determinant of replacing the vars coefficient column with the constant column, finding that determinant, and then dividing it by the determinant of the original coefficients. We're just going to use it on an easy problem. We're not going to go to something big like a 3x3 or a 4x4. Once again, by hand, that would be kind of crazy and kind of hard and more complicated than it needs to be. But let's see if we can at least understand how it works with, oh, it shows snazzy notation. Whatever. You guys don't necessarily need that notation. Instead, just need to know how to do it. So if we were to solve for x, and if we were to solve for y, they're both going to be fractions. What's going to be in the denominator of both? 4. Isn't it going to be this, guys? You don't necessarily need to write down the formula. You can if you want. We're just going straight to the example. Right? It's the determinant of the coefficient matrix. 4, -2, 3, -5. What's going to be the denominator of this guy? Same thing. 4, -2, 3, -5. Okay, numerator. This is where it gets tricky. For the x, who do we take out? Yeah, take out the a's and put in the 10 and 11. For the y's, we take out the and put in the, so we keep the 4, keep the 3, but put in the 10 and 11. So see how I'm putting the constants in the column of the variable we're solving for? How do we finish? We take some determinants, yeah? Now, once again, this is easiest for the easy ones because we can just do main minus opposite. If it was 3x3s from a 4x4 system, from a 3x3 system, it'd be nasty. Thomas is already going -50 plus 22. It's going to be -28, yeah? -50 plus 22. And then the denominator, I have -20 plus 6, which would be -14. If we're right, x equals 2. Y equals 44 minus 30 over -20 plus 6. And y equals -1. Once again, is this the most efficient way to solve a 2x2 when you're a human? No. Or a 2-variable system when you're a human? No, not at all. Do substitution, do elimination. Ugh, that's not even pretty though. Who wants to substitute on that guy? Elimination, we have to multiply the top by, maybe a +3, bottom by a -4. Oh, long story short, 2, -1. This one lets us just play with the numbers, which is kind of cool. So we have 8 plus 2 is 10, got it. And we have 6 plus 5 is 11, done. Cramer's rule. Once again, it's easiest on the, oh well, but it is another method. Ooh. Why is it nasty? We have a 3x4. Why does it say if possible? I'm just trying to introduce you to an idea. Why does it say if possible? Can anybody think of an impossible system? At least it'd be impossible with Cramer's rule. What would it take to be impossible if we were trying to find x and y and z? And what would make the denominator equal to 0? The determinant is 0, and which determinant would we be looking at? A's, B's, and C's, right? The guy I have the coefficient matrix, right? So the question is that we have to ask ourselves, does that determinant equal 0? Kiddos, throw it in your calculator real quick. I'm not going to make you go through and do 1, 2, 3, 4, 5, 6. No, it wouldn't be that bad because these are all the same. So 1, 2, 3, 4 different 3x3s just to solve this system of equations when we have row echelon form, etc., to do it for us or to do it in a more efficient way. But just throw in that 3x3. My question is the whole if possible. It'll always be possible as long as that determinant is not 0. So my question is not what the answer is, but instead, is it possible to use Cramer's rule, yes or no? Are we getting better at doing matrices? Second reciprocal button, edit, make it, DET. What'd you guys have? Okay, it does not equal 0. Instead, it equals 33. Which means I could right away put 33 as the denominator. Now, I'm not even going to finish this problem. The long story short is, yes, it's possible. My question is, if the determinant of that variable, of the coefficients of the variables, if the determinant was 0, my question is, okay, Kramer's rule would not be possible, and we see that. You can't divide by 0. My question is, would it be possible to use any other method? Why? Or why not? Okay, we know other methods. We could try row echelon form. We could try making a matrix and using RREF, reduced row echelon form. We could try being a human and making up our own way as far as whatever order we want to do it in. But can anyone tell me why, if the determinant of the coefficients is 0, there is no solution to the entire matrix itself? What's true about when determinants are 0? That's been a thing recently. Look in your notes. If the determinant of a matrix is 0, then there is no inverse. Wait a minute, didn't we see that the way to solve a system using matrices and inverses? Oh, remember? Couldn't we write this using that? And I know your homework had you do it once or twice. Couldn't we write the 5, -4, 1, -1, 2, -2, 3, 1, 1, times the variables, like we're factoring out the x and y as z from matrix multiplication, equaling -14, 10, 1? Isn't this really just one big ol' equation, right? All the coefficients times all the variables equal all the constants using matrix multiplication. What's the only way to get to the variables? Inverse. Just like we've done in any variable equation that we've ever seen, the only way to get to variables is to do the inverse operation. Now, can I just simply divide? No, that's not how matrices work. But if there is an inverse, then I undo this all, do the inverse to both sides, and get the variables. Your homework had you play with that a little bit in 8.4, maybe even 8.3. But the idea being, if the determinant is 0, there is no inverse, the equation cannot be solved. Does that make sense? We're still pondering. But anyway, that could be something where if you're trying to build an efficient program, and if there's something where perhaps you're trying to find determinants or you're trying to solve systems, etc., you would put this as the very first thing to check and say, hey, let's just check the determinant. If it's 0, done. Ooh, that makes it more efficient right away. And if it's something other than 0, oh, Kramer's rule says I'm halfway to an answer. Let's just finish it off. Once again, I think the programming in your TI, if I'm correct, which I should research this and refresh my knowledge, but I'm pretty sure it uses reduced row echelon form in solving. Well, I mean, I guess you guys use it when you do the RREF. But theoretically, if you had something like Wolfram Alpha trying to solve a system of equations, maybe it would be using something like Kramer's rule instead. Okay, Kramer's rule. You saw it. It's a thing. We saw how determinants can apply. It's kind of cool, but it seems kind of tedious if you're trying to ever do anything by hand. But some of you are like, I kind of like that whole thing with the 2x2. Maybe I'll steal that. Because elimination can get kind of annoying, and substitution sure can get annoying. This one's going to be a bit nicer. This one's going to be a bit nicer. This one says we can find the area of any triangle with 3 vertices using a matrix. That's interesting. You're like, well, wait. A triangle, 3 vertices, no big deal. Why don't we just do 1/2 base times height? Ugh. If you had any 3 vertices on some Cartesian plane, what would you have to do in order to do 1/2 base times height? You have to find the distance, right? Because that'd be a base. Find the distance between those 2 points. Then you have to find the midpoint? You can't even say the midpoint. We have to find the point that's directly across from this guy, which might be the midpoint and might not be the midpoint, but then we'd also have to figure out a way to find the altitude, to find the height, and then plug into the formula. Like, wait. We have Huron's formula. Huron's formula says just get all the sides. Okay, fine. You have to find this distance and this distance and this distance. And then use Huron's formula. Ugh. Or, don't even go to the law of sines one, because that one you need an angle. Ugh, let's not find an angle. Or you just go ahead and say, hey, take each of the points. It doesn't actually matter what order you put them in. Just take each of the points, xy, xy, xy. Continue to make it a square matrix by adding in ones. And then multiply by 1/2 and either a positive or a negative. Whatever sign makes it positive. You basically just need to think about whatever this determinant gives you, cut it in half and make it a positive number. Pretty much what's going on. So if you were to have something like the following, you could go through doing lots of different distance formulas and then Huron's formula, or you could just say, hey, whatever, I have a better way. The better way says, take your points in whatever order you want. What do we do to finish it and make it square? Now what? Find the determinant. What row do you guys want to use? Third column? Okay. Third column, positive, negative, positive. So I have 1 times the remaining 2, 2, 4, 3. Positive, negative, positive, negative. 1, 0, 4, 3. Then I have 1. Times the remaining. 1, 0, 2, 2. 6 minus 8, yeah, it'll be negative 2 times 1. 1 minus 0, just 1. Times the negative 1 is still a negative 1. 2 minus 0 times 1. 2 minus 0. 3 minus 0. I have no idea what I'm doing. I think I was looking at, I don't even know what I was looking at. Something. 6 minus 8, 3 minus 0, 2 minus 0. Got it. Cancels out. Negative 3 halves. Wait, can an area be negative? Okay, so from the very beginning, it's technically a plus or minus. Basically just says, hey, do whatever you need to do in order to make it a, take the value, make it a positive. If you want to think of a big old absolute value on the outside, I guess you can, but why don't they use that notation? Because I'm using the absolute value bars to denote or to show, to signify determinant. So that's why not. That's why not. Now, here's a crazy one. If this is the formula for area, when or why or how, what would be going on in the picture such that this would be 0? How can area given 3 points ever be 0? Don't 3 points always make a triangle? And every triangle always has area? 3 points will not make a triangle are in the same line. Collinear points will not make a triangle if they're in the same line, aka the area will be 0. If the area is 0, this little guy has to be 0. So we could check whether 3 lines, or I should say 3 points, are collinear by saying, hey, let's find the area, but let's forget the 1/2 thing and just take the 2 points. Sorry, the 3 points. We just have to find the determinant and say, hey, is it 0? If it's 0, yeah, they're in the same line. They can't make a triangle. If it's not 0, it makes a triangle. Can't be in the same line. Now, guys, what was the section title for 8.5? Just how can determinants be used? It can be used for Cramer's rule. It can be used, they can be used for areas of triangles, which can also be applied for whether or not 3 points make a line. There's one more big, ooh, hey, there you go. There's one more big application. Whoa! What we're going to be talking about tomorrow, which shouldn't take us all of class unless we have a lot of fun with it, but what we're going to be talking about tomorrow to finish 8.5 after covering 8.4 homework questions is how can we code messages with matrices? Bye, cool kids. That's the last thing in chapter 8. You guys can do everything in 8.5 except for the coded messages. Bye, guys. See you laters. Yeah. Am I going to what? The collinear one?